Yeah, there is up here on the upper left corner. It says recording.
Okay.
So so let's welcome Dr. Rohan Paul to give our seminar. Dr. Paul is an assistant professor in Pankaj Gupta Young Faculty Fellow at the Department of Computer Science and Engineering, Indian Institute of Technology, Delhi. His research program is aimed towards capable service robots that can perform complex tasks alongside humans. Dr. Paul was postdoc at MIT working with Nicholas Roy. He was at the Toyota Research Institute and NSF. He got his PhD from Oxford University working with Paul Newman. His work won the Best Paper Awards of RSS 2016, IRAS 2013. It was also in the finalist for Best Vision Paper Award at ICRAS 2010. He is a recipient of 2 national awards from the government of India and was named one of the 35 global innovators under 35. So please go ahead.
Thank you, Zhang, for such a generous introduction. I will just load up my slides just to ensure you can see, if you can confirm if the slides are visible at this time. Are the slides visible?
Yes.
Okay, great, thanks. Let me just position. Great, thanks very much. I'm deeply honored and privileged to be participating in the CMURI seminar series. When I was a graduate student, I listened very often to RI seminars more in a tutorial mode. I never imagined that I'll be, speaking as one of the speakers later in my career. So I'm deeply, honored and grateful for being here. I also recognize some of my mentors here. So Jean, I regard as my mentor. Jean, very nice of you to also be participating here. All right, so the talk is about human-robot teaming. And essentially, I'll share some of the work that we've been doing for the last 5 years or so in enabling humans and machines and humans and robots to work together. And this talk explores a model of intelligence for making that happen. So as a historical context, since the very early beginnings of AI and robotics, our field, we've been trying to create artificial intelligence agents that can sense, reason, and act intelligently in the environment. So right back in the days of Shaky, there have been attempts to create systems that can take in high-level objective, perform reasoning, synthesize behaviors in the context of the environment in which they are situated. And this is perhaps one of the earliest demonstrations of sort of end-to-end process going from high-level objectives to behavior synthesis. And since that time, there's been obviously significant progress, and the systems have transitioned from laboratories to factories, and we see a number of modern-day examples, right from enabling extraordinary science in going into places which have not been explored, to autonomous driving is another technology which is rather at the boundary of what we can achieve in the laboratory and what the industry is now readily adopting, as well as I think also factory automation and logistics automation are prime examples where autonomy has been pushing the frontier in being realized in the real world, which is unstructured, uncertain, and in which these machines need to operate, confronting all of these uncertainty and perform tasks that they are designed for. So if we just reflect back on some of the key pieces of technology, particularly in the last 10 to 15 years, there've been substantial progress in a couple of very important building blocks into these systems. So particularly progress in efficient inference, enabling answers to the following questions. Where am I located and what is around me? So the progress that has been made in the problem of simultaneous localization and mapping and state estimation in general has been one of the main cornerstones on which this modern day robotic platforms and systems that we see are being realized. That's a problem that we've made substantial progress on. And the kind of maps that can now be generated through multi-sensor fusion, LiDAR, visual, and others are crisp, and we can also almost get very realistic, beautiful looking maps and positioning out of many of these systems. These systems not just are in short areas, which is, say, the New College data set being visualized on the top left, but also operating at vast scales at the order of hundreds and thousands of kilometers. And we today have the capability of performing loop closures and fairly large scale localization. Apart from that, what is around me is another problem where we have significant progress, particularly post 2015. With the advent of very robust methods of function approximation, which have enabled us to understand the environment in terms of semantics, in terms of what is drivable, not drivable, what are the entities around, allowing the machine to have tremendous situational awareness as it is moving around. And I think the third piece where we've made significant progress is around, in some sense, learning to control or learning manipulation skills. Those are the images on the bottom right, where we're seeing a clamp passing task, and the robot is able to accomplish fairly sophisticated bends, etc. And this sort of a motion has been realized or learned from direct human demonstration. So being able to insert use tools, perform fine-grained manipulation skills, largely skill learning, has been another jewel in what, as a community, we've been able to accomplish. And all the work in reinforcement learning applied to control and being able to control robustly and improvise, that has been very significant progress has happened in these areas. Now, if you move forward, robots have been transitioning from laboratories to factories to outdoor environments, and in some sense are getting into the human ecosphere. So the human is there somewhere. Robots rarely operate alone. The human being is there either as the object of interaction, say the Skydio drones on the bottom left, which is following a person moving around, to other domains in which the human is the supervisor. So in a factory, we would like machine, most commonly, there is a human operator which is supervising operations or providing some level of detailed guidance of what the platform should be doing. And also in an autonomous car kind of an environment, the human is there, watching over a lot of the time is there. So as we see these progressions, robots need to understand and perform tasks in human cohabited spaces. And I'll focus on two aspects of this. One is the ability to understand what the human is intending. What is the task that the robot needs to perform is one aspect of the story. And second, as robots now start operating in human-centric environments, we expect them to perform tasks that we would otherwise be performing. We would want machines to be able to do assembly. We would want them prepare breakfast or perform some sort of inspection task and so on and so forth. There are these semantic tasks that we know can be undertaken, and we would like machines to be able to do that. And those are going to throw up some interesting challenges, as some of them I'll talk about in this presentation. So in this particular view, let's draw a little diagram of what we want an autonomous agent to accomplish. We postulate that there is a human commander which is providing a high-level specification of the task. Let's say there's an instruction of what the task should be performed, and we expect the robot to synthesize a sequence of actions to accomplish the intended goal from the human commander. And the robot must synthesize such a plan based on the context, based on what observations it has of the environment, as well as some prior domain knowledge that might be available through experience, either encoded semantic knowledge or other experience gathered by the agent autonomously in the environment prior to being provided the instruction. And since this talk focuses largely on high-level autonomy, we would assume that there are feedback control systems under the hood that can realize high-level actions which have been decided and what the robot is trying to do, to perform. So at a very high level, this is our estimation task. We want to estimate the most probable plan given in the context of the instruction, what has been instructed by the human, given the observations and the experience that the machine has. So I would argue that for certain kinds of tasks, such as, say, local movement or short-range tasks, this is something that is today learnable. We're able to learn skills, we're able to plan motions. For certain tasks, this has been possible. But as we scale this to more complex tasks, particularly in human-centric environments, we start noticing that there is a problem in being able to estimate this distribution directly. So let's see why. So let's imagine we have, say, the Baxter robot, and we want the machine to be able to, say, prepare breakfast or do some sort of an assembly in the environment, or if we have a ground vehicle where we would like the vehicle to approach a particular landmark or a region of space, following a road to the parkland kind of an area, if you imagine that that's the kind of task that we are giving. We reason in terms of high-level constructs, which are symbolic, which is pick up and apple, and how the apple should be, all the fruit should be assembled, how the tray might be useful for transporting, things of that kind, as well as in the navigation task, what does the following of a road mean? What does approaching the park really mean? So we have these high-level constructs that we have acquired through experience and other things, for which we have linguistic labels as well. But for a machine, this really does not exist. For a robot, it lives in the land of cost maps and point clouds, which are noisy, and it's an overly complex representation. So there is this gap, in some sense, a semantic gap between the higher level constructs, which we have embedded in our heads, which we're used to reasoning with, which is very amenable to sort of symbolic reasoning, and the continuous noisy low-level sensor information, low-level sensor and control space in which the robot is operating. And it's really this fundamental gap that exists between the symbolic representation, very amenable to reasoning, and the real-world noisy representation that the robot is working with, which is crucial to be bridged in order to make progress and be able to perform human-guided tasks, or tasks that humans expect robots to be able to perform. So our agent, which is given this high-level instruction and needs to execute or synthesize behaviors in the context of its experience and what it is seeing in the environment, must somehow bridge these things. It must somehow connect the high-level or ground the high-level symbolic constructs to something that have a reality in its own little continuous and noisy control and action space. And this crucial connection between the high-level symbolic constructs and the real world represents, in some sense, the world model, represents this grounded connection lives in the world model. And this representation of what the world state is and how the world is behaving allows our agent to factorize the distribution into simpler constructs. So let's say that we would hypothesize the existence of a world representation or a world model, which can be acquired by past experience and observations. And once you have access to that, it becomes easier for us to understand and reason about the high-level objectives given by the instruction itself. So that's, in some sense, becomes like a more promising factorization and possibly a path forward towards pushing our boundaries towards realizing high-level tasks, being able to perform high-level tasks as instructed by human partner. So the remaining of the talk, I'll be talking about this world model and try to tease out what are some of the elements which are required and present some examples of what we can do if we are able to learn these grounded high-level representations in our world model. So let's talk about two inference problems, and let's begin by looking at inferring what the task is. Can we understand or infer what the task is from linguistic, from language and from vision? So the question is, why language? So language is a rich and intuitive way for humans to communicate, share their mental model, provide situational awareness, and provide objectives or share intent. So there could be simple instructions like prepare my breakfast, Or it could be more complex to say that, well, today we are assembling engines, and this engine requires parts of a certain kind. Hand me the engine parts so that I can start assembling, right? Or slightly longer instructions involving spatial relations and other things, like go to the fire hydrant behind the traffic cone. The image on the bottom right is actually from NREC, from the RCTA program. And this high-level instruction, somehow we would like the robot to be able to interpret in terms of its world representation, and then be able to synthesize appropriate behaviors to satisfy this instruction. So given the task at hand, our primary piece of technology is going to be a grounding graph. The grounding graph is essentially a probabilistic model. It's drawn in a factor graph manner, which relates the input instruction. The linguistic construct navigates it towards the cone and relates the input language with things in the robot's world representation. So let's imagine we have a simplistic map in which we have the robot, we have a couple of objects, say a cone, a barrel, or a traffic sign, and we would like to infer what is the constraint, what is it that the robot should do. In some sense, relating or being able to infer or relate the linguistic instruction with specific entities in the world model. And this probabilistic association between the language and things, the things in the world model is mediated by a correspondence variable. In the sense, we would like to maximize the correspondence between language and entities in the world. And reasoning about the entire instruction is a little difficult, so we can leverage sort of the well-understood power structure of language to structure this inference in a more tractable manner. So this big giant, like a simple factor graph that relates the entire instruction with entities in the world, can be broken down and arranged in terms of the power structure. So we can first infer the cone, and then navigate depends on the interpretation of what the smaller phrase, the child phrase, was referring to. So once we infer the cone, we should be able to then infer, navigate to mean a constraint that connects the robot with the particular object of interest. And we can take this process forward. We get like a longer instruction, say navigate to the cone behind the barrel. We can decompose this in terms of the underlying power structure and estimate the most likely correspondence and infer the appropriate groundings in terms of, say, the barrel relates to the particular object. Behind means a certain region of space behind the barrel. To the cone means a particular cone which is related, which satisfies the spatial relation in the context of the barrel object. And finally, navigate there can be various interpretations. Navigate can be interpreted as a particular control trajectory or a path, but it could also be at a higher level, be represented as a goal constraint. And once we've inferred the goal constraint, we can hand this to a planner which can synthesize, like a low-level motion planner that can synthesize a platform-specific motion plan to accomplish what the instruction is implying. So that's nice. So this gives us a way to relate language with specific constructs that the robot can observe in this environment, assuming an object-centric representation, and being able to relate the input language to these constraints provides us a path forward to be able to provide these constraints to another planning routine which can synthesize appropriate plans. So the video on the left.
Put the tire pallet on the truck.
Is from Stephanie's work a couple of years ago, and she's been a pioneer in this area of introducing grounding graphs. And here you see the input instruction of putting the tire pallets on the truck being broken down and the appropriate groundings being inferred, and the forklift is finally executing this plan. It picks up the appropriate tire pallet, and then if you sort of move forward, it'll lift and bring the particular objects and place it on top of your truck. The way back in 2011 was a pioneering work, and then following that is, say, a piece of work on distributed correspondence graphs that examined the particular inference being done in generalized grounding graphs and introduced symbolic representations that make the inference move much faster in terms of being able to decouple the meaning interpretation part from the motion planning part. So here you're seeing the instruction, a very simple one, pick up the gas can, where the Roman platform is then able to ground that to the particular object and then synthesize the particular motion plan to vertically lift the object. So that's nice. So the grounding graphs give us a way forward, being able to relate language with specific goal constraints, which can be again given to a planner. But what we don't have at the moment in our machinery is the ability to reason with collections of objects. So let's say we want the robot to be able to pick up the middle block in the row of 5 blocks on the right. So what is the interpretation of a row of blocks or a group of blocks or a circle of blocks, columns, etc.? We don't really have a notion because these are abstract concepts. They are hierarchically represented. These are collections of objects. And till now, we've only seen how do we work with specific objects and how do we relate language immediately with constraints on different objects. So let's go back to our grounding graphs and see how do we actually introduce a notion of abstraction in these models. So let's say we want to now represent the grounding for a row of 5 blocks. And notice that abstractions really involve reasoning about large sets of objects. A row of a certain blocks means a certain number of objects are there. And hence, once we inject these particular constructs in our grounding graphs, they start looking more complex because now we have to express all possible subsets of objects, etc. And how do we represent these except by connecting these probabilistic relationships? And in some sense, we are now starting to reason in a more complex factor graph where we have to model these abstractions. So that's not very good because this is going to make learning and inference difficult. So what do we do? So the path forward is to introduce explicit notions of abstraction by introducing hierarchy. So if we introduce a particular representation for an abstraction which depends hierarchically upon the expression of the blocks. For example, if you want to infer the row of objects or row of blocks, we first perform reasoning on blocks and then infer or reason about abstractions such as rows or groups or circles of objects. So in a sense, more formally, when we introduce an explicit representation for an abstraction, we're really creating a Markov boundary, which decouples the inference in a particular manner. It simplifies our inference because then we are naturally factoring our model hierarchically in terms of expression of concrete objects and then reasoning about abstractions subsequently. So that's what the grounding graph now starts looking like. Instead of having, say, a particular sort of flat representation in which we are essentially just reasoning over objects or blocks, we now introduce hierarchical constructs which are connected appropriately to expression of concrete groundings, which are things which live directly in the robot's world representation. So that's nice. It gives us we can make progress with this model. So then the question is, how do we learn, perform any form of learning in these models? So the way we can proceed is to generate aligned corpora where we have certain world models or simulated world environments in which the robot is operating. And we get human annotations where humans are asked to provide necessary instruction for the robot to displace a particular object in the environment. And that gives us the pairing between language and entities in the world. And by seeing enough of these pairings, we are able to train these models. And once we come to training in the particular work, we used a log linear model. That means there were hand-coded features which look at both linguistic and physical attributes. But in subsequent work, these assumptions have been relaxed, where feature learning is part of the learning process itself. So the video here would show the instructions being executed. So picking up the middle block in the row of 5 blocks, the robot infers the collection on the right side, and then reasons about what is the middle block within that abstraction. It happens fairly quickly. This is displacement of the farthest block in the column. And you can do it more and more complex. The second farthest block, the nearest 2 blocks, things like that. You can start reasoning with sort of substantially, we can now reason with significantly more complex instructions than what we could do with the vanilla grounding graphs formulation. Okay. So then the question is that what happens if I provide a language instruction that refers to objects that we've not seen so far in our world model? So let's say if we have a turtlebot and there are a couple of objects in the environment, one of them is known. So the jar is known, but the other objects which are not there, but for which there is no association with the linguistic construct as yet in the world model. So there's like an unknown object which is there. We don't really know how to refer to. So if the language starts referring to essentially constructs which cannot be grounded, so they're ungrounded literals, or there are unknown detections for which we don't have labels, then what do we do? So the way we can make progress on this is for the robot to perform exploration. So if it hears, gets an instruction which talks about an object which it has not seen before, it does not have a model for before, then it can start trying to gather more information to see whether it can ground this to some other unknown object in the environment. And that's what's happening here. In this case, when we say move to a particular box, it saw the jar, it did not know about the box, and it starts grounding to that. And another case, if it only has known objects in the environment, then it performs visual surveying. It's in a sense, it's expanding, but that's a cue for exploration to gather more views to see where the ungrounded object is. And this process is continuing. So it's moving, and it sort of has updated what it had initially acquired as the new models, and then later on it sort of figures out where the unknown objects is, so that it can then associate the linguistic construct with that, and then perform the appropriate navigation task. So what this allows us to do is to essentially have, in a sense, a plastic world model. That we start with certain number of constructs, but with interaction, we are able to associate unknown pieces of language with unknown detections in the environment and retain that information for future. So the model grows over time, so we're able to get more objects in. So then the obvious question is, what if there's ambiguity, right? So if there's ambiguity, then we can engage in dialogue. We can talk about or elicit more features from the human to say, can you describe the object, right? So if you get attributes such as blue or cylindrical, or it has a white lid, then that additional the additional pieces of language provide additional disambiguating cues from which we are able to collapse the distribution to a particular object among many candidates. So this was about being able to handle constructs that we've not seen so far. But the kind of instructions or the tasks we considered were largely where the instruction could be directly interpreted into the world model which is there in front of the robot. So in some sense, there was no notion of time here. In a sense, there was a snapshot of the world in which the language was overlaid or related to specific constructs in the environment. And some of it involved gathering future information with ungrounded literals, but largely we didn't really have, say, a temporal notion to our model. But often we need to reason about time, and we need some model of time. For example, if the Baxter robot observes a person putting down a particular box in its workspace, and after having observed this video, what if we ask this instruction? What if we instruct the robot to pick up the box that the person put down? Now, we didn't really have a past in our model, so we have no ability to ground the box that I put down or disambiguate between two boxes, reasoning about what interactions happened in the past. We don't have that ability. So what we can do here is to leverage some of the work in the vision language community, and this is work by Andre Barbu, where the approach tries to relate or ground natural pieces of language by inferring a certain logical form. So the block that the person put down or the box that the person put down can be sort of semantically passed into constructs, symbolic constructs such as block X, put down XY, human Y, which naturally expresses the semantics of of the interaction, but also provides the X and the Y's as constraints. Like whatever has to fill in X must satisfy the appropriate ordering in the other predicates as well. And on the vision side, we have detections. We have various object detectors that fire across these images. So what if we could extract tracks from these raw detections in such a way that they are maximally compatible with what the language constructs is dictating? So the idea is that can we estimate now a correspondence between the particular tracks which have been observed in the continuous video with the language construct and say the maximal, let's compute the maximum likelihood association between X and Y and the particular tracks. And those would now correspond or give us, say, a disambiguating cue of which of the boxes was put down by the person. And once we connect this with the machinery we have already in our model, that provides us a way in which we can use language that talks about the past to, in some sense, go back and foveate on the observations that we already have. So the language is providing, say, these constraints that once these constraints are appropriately grounded in our past observation, gives us exactly the semantically what objects or what concepts that that language is actually talking about. So this is the video of the same experiment. The robot observes a person put down a cracker box on the workspace. And then we utter the instruction, pick up the cracker box that I put down. And the robot now must disambiguate between the box on the left, the cracker box that I put down, the box on the left or the box on the right. And by using, again, reasoning with the instruction that referred to the past, we can go back and resolve that in the past observations. And then it takes a little bit of time because of machine planning. The robot is able to disambiguate and figure out that it's the box on the left and not on the right, and then vertically displaces that. Okay, so this was about being able to ground instructions, in some sense, learn models of the past and ground towards observations that happen, towards interactions that happen in the past. But oftentimes, we also might need to retain some other linguistic information from the past that might be used a bit later, which may not have a physical manifestation. So let's say I utter an instruction that the box on the table is my snack, or a particular fruit is my snack. Now, my snack is an abstract relationship. It does not have a physical grounding as yet. But later on, I might refer to this particular constraint saying that pack up my snack or bring me my snack. So is mine is the predicate that we need to retain somewhere in our world model, and so that the later instruction can then use the factual information that we received in the past to be able to resolve or appropriately ground to the object. So in order to do that, we do need to keep track of a certain set of variables, and we will call that as K, and the K's have been highlighted on the top of the slide, saying that there is the linguistic information has given observation for certain discrete variables. And we can update likelihood based on some sort of a sensor model of saying that once the language asserts a certain fact, those distributions go up. And that those sets of linguistic variables, maybe they can grow over time when we have new facts as well, provide as another piece that we retain as context or as prior experience moving forward. The advantage is once we utter the instruction again, we have another set of variables to condition over. And once we have that conditioning, we should be able to resolve an instruction that refers to a factual piece of knowledge later. So let's see here. Here you'll see my colleague say,
Alexa, tell robot the box and the can are my snack.
So Naomi asserts that two of the objects on the table are my snack, and the third one is actually
Alexa,
not. So,
tell robot pack up my snack.
And later on, if she says that, well, pack up my snack, we should be able to say that, well, these two objects constitute this collection are associated with a is mine or is my snack predicate, and hence we should be able, we are essentially going to pick up these two objects and put them appropriately in boxes. Right, and the robot then picks up the can, the spam can, and the cracker box, assembles that into appropriate destinations, puts them away and leaves the banana because the fact was not asserted for that, and then we have an uninformed distribution for that, so we can ignore that and successfully accomplish, fulfill the task at hand. So we call this temporal grounding graphs because that brings in a notion of time. We've learned to go back into time, or in some sense also be able to remember facts, that those declarative statements that might be used later once we condition on that to resolve future instruction that we might receive. So let's turn our attention to the second half of what we set out to do. Initially, we wanted to interpret language, right? Or interpret what the task is, because that's like a fundamental requirement for a robot operating in a human-centric domain. But language understanding is sort of intimately tied with what we understand about the world. And knowledge about the world is fundamental in being able to both understand and reason about the instruction. And this is going to be handy, particularly in environments where we have some form of incompleteness, some aspect of the world is not observed directly, for which we need to make certain inferences, or if the language itself, or the task itself, is ambiguous. So having this background knowledge will essentially allow us to fill in these gaps in our knowledge to be able to successfully accomplish the given task. So let's take an example. So let's say we're doing, again, let's go to cooking domain and say we want to prepare a snack. And there are various ingredients that we might need to assemble and bring, etc. It's very unlikely that we will say that, say, for a burger preparation task, that once we take out the patties, that it is necessary to take out the patties from its container, from its packaging. No one explicitly says that, right? We just assume that we are not going to put that entire the carton kind of a thing on the pan and start cooking. We know that innately, and the reason we know that is through common sense and with experience. We know that contents need to be explicitly taken out from the containers before we put that into the pan. So the question is, if I say prepare a snack, the robot needs to somehow being able to fill this certain other prerequisites before the behavior can be synthesized appropriately to accomplish or to successfully complete the task. So the question is, where does this knowledge come from, and how can we, get this piece of knowledge? So one way is, say, by reading. So this is from the movie Short Circuit, where you see a robot who's trying to help in the kitchen.
Input, Stephanie, more.
There isn't any more. You've read everything in the house.
Ooh, animal, mammal, skunk,
Oh,
vessel, container, drinking glass, pasta,
Yeah,
semolina, spaghetti.
Right, so I think it's like a science fiction thing, right? So what it's trying to really say that the robot doesn't know how to cook, so it starts reading and then reads sort of everything which is there, and then starts recognizing certain constructs. That doesn't really do a good job, but at least tries to get access to this declarative knowledge that lives in books, and then starts to perform a certain kind of a task. So our machine learning hasn't really made all that much, say, what short circuit we would like short circuit to do, but we can do some kind of some approximation to this. So there are corpora where there are descriptions of tasks and how tasks should be performed. So WikiHow is one example, which has a number of recipes, a number of short plan sequence, largely, which dictate, well, that to, say, prepare a milkshake, this is what you do. You put a banana into the blender, you add milk, etc., etc. How to set a table. There are instructions which are provided. Obviously, they're noisy, they might be incomplete, but at least there's some relational information which is provided that how things should be sequenced in order to accomplish a high-level task. And then there are other sources like ConceptNet and WordNet that have taxonomic relationships. So the question is, can we use this large source of written down declarative knowledge somehow to fill aspects of the plan that might not be mentioned? So where we can proceed with this is to use a machinery like Markov logic networks that essentially have discrete constructs and learn probabilistic co-associations between symbolic constructs. So let's say by observing that empty cartons are discarded typically in a trash can, we can try to make predictions later that if you see something which is empty, most likely destination is a trash can. They are unlikely to be stored appropriately. And the same is not true for, say, pieces of fruit. Pieces of fruit are often stored into fruit baskets or something that is there in the kitchen and not sort of thrown away. So by being able to learn a certain probabilistic model, we should be able to make inferences about certain set of variables, condition on certain other sets, if we have access to corpora or data set that has some of these observations embedded in it. And once we get online a particular instruction that refers to some of those variables, those are observed within language, then the remaining can actually be inferred to a certain extent by this learned model. And then that should be able to fill in certain pieces in the high-level behavior constructs, and then the behavior could be executed. So let's take an example for this, where my colleague is going to ask the robot to prepare breakfast. So the robot doesn't know what breakfast is. It doesn't really ground, so it engages in question answering stage. What would you like to have? And then my colleague is going to say, well, prepare some cereal and some fruit. So let's play that.
Prepare breakfast.
What would you like to have?
I want cereals and a fruit.
Right, so the robot first picks up the cereal box because it can be immediately grounded. But what it's doing now is the interesting part. That cereal is often co-associated with milk, and milk is typically found in a refrigerator. So it's like a mini refrigerator where the robot is trying to look for the milk and sort of makes predictions that, well, that certain other entities as well, but refrigerator is where the milk is most likely to be found, then observes that through this camera and then says, well, this is the object that I was looking for. I can ground to it, and then starts to extract that object from the refrigerator and fills the task, completes the task. So it will bring that bottle out and put it on the tray and finish that part, and then finally it has to get the fruit, so it will move and then finally fetch the fruit as well, and then the breakfast plate in some sense is ready. So the ability to fill in the missing pieces, so being able to infer the cereals go along with milk, and milk is often found in the refrigerator. Textual data. So we talked about common sense knowledge that, say, cartons are often discarded, or the milk is found in refrigerators, etc. And that's sort of useful for us to fill in missing pieces and instructions. But there are other pieces of common sense knowledge as well, particularly relating to how tasks should be performed in general. So let's say if I ask a robot to bring me all the cups from, say, the kitchen. Right? So one motion plan is to actually go fetch one cup, bring it here, give it to me. The robot goes back, then fetches another one, then brings it back, then fetches another, brings it back, fetches another, and so on and so forth. So that's one way to do that. Let's say that even if the robot has to go to a certain elevation and uses a ladder and things like that, right? So in the cup case, the obvious thing that we would do as humans is to use a tool of a particular kind. So we would use trays, and we could use, we could put all the cups into the tray and then carry the tray. In one shot, we would get a more effective motion plan. So this is like a planning abstraction of some kind that we've acquired by experience. So the question is, can we actually acquire that in our learning system? Can we actually infer a particular tool use, which is contextual and task dependent, and that allows us to essentially perform tasks which are more human-like, and human-like that those are likely to lead to more effective plans. So this is emerging work in that area where what we can do is to create a virtual environment where humans can be asked to in some sense, teach the robot. So the human is asked to instruct this little agent, so this Haskell-Plus UF5 manipulator, in a virtual environment, which we can set with a variety of objects, and objects can be inside, on top of particular locations, etc. They could be inside a refrigerator, or they could be a cupboard, things like that. And then we ask different kinds of goals to be accomplished. So let's say that the goal is to bring certain sets of objects to a particular location. So the human is to specify a certain plan, a certain rollout. So get particular object from the fridge, then put something on top of another thing, or put in the container, bring it back, so on and so forth. And we would hope that once we are asking the human to do, they would start making creative use of tools, like boxes to carry, or trays to carry objects, or ladders to negotiate elevation, or use stick to actually tree somewhere where the robot arm cannot directly use, etc. So some of this innovative tool use can come in handy, and it sort of starts appearing in these planned rollouts from the human. And once we have this corpus, the next thing we can do is to, in some sense, learn a policy, learn like an imitation learner, which can learn a policy trying to imitate what the human did. And in a sense, try to, in some sense, learn this common sense knowledge, learn this predictor that if there are a large number of objects in a particular area which have to be brought to closer to the human, then an effective way to transport is actually by using a box or a tray. And this particular learner is realized as a neural module, which estimates a likelihood of over certain symbolic actions which are predicated on objects. But by learning dense representation, by making use of conceptual dense representations derived from, say, ConceptNet and WordNet, etc., we can show some sort of a taxonomic or semantic generalization. So let's imagine in our plans, we have seen trays being used for transportation, but at runtime or later on, we observe not trays, but boxes. So can the model actually generalize to a box without actually having seen that before? And the reason why we are able to do that is because of the dense embedding, as well as the learned representation of the world model, being able to notice that if you have a large number of objects to be transported, that's like a queue for tool usage, and may not be very effective if there's only a single object to be transported. So this kind of a generalization, more taxonomic to unseen object types, or being able to use unseen tools, as well as to environments that we have not seen before, is something that this model is able to do. So this is also still in simulation, sort of still work in progress, but it sort of provides an exciting direction in which, let's say that if we are able to back out some of this common sense knowledge, maybe it's embedded in the weights of the neural module, which is providing us this policy. But if you have access to this symbolic data, then it is actually possible to learn some of these things. And one way this is sort of useful is, say, if you're doing task planning in a realistic human-centric environment where you have lots of objects, the plan possibilities are fairly large. And what this abstraction is able to do, if you're able to predict that a tray is going to be useful, in some sense it compresses the branching factor. Right? So it sort of says that, well, there's a certain likelihood that the satisficing plan is likely to go through this abstraction. So we should be able to bias our exploration, or at least this plan search, in a particular towards something that the human has shown before. Still, there's effort required in translating these results from simulation to the real world, but this is an exciting initial direction to explore. So we looked at two methods in which knowledge was acquired. One was background sources of knowledge. The other one was around using explicit human demonstration. But there might also be other things that we might need to do as the plan is being executed in practice. So as the plan is being, we have an instruction, we need to execute a certain plan, but there's certain aspects of the world model that we don't have access to. Let's say we have a clearing task. And in the clearing task, we are supposed to throw away empty cups into the trash can. And we don't want to throw the cups which have something in them, which have contents in them. And clearly, if there's a lid on top, we don't know the internals of the cups. So what do? So we have the instruction to say clear, and we assume, as we have some prior to say, well, they might be empty, but we really don't know. So the thing that can help here is physical interaction.
The cups on the table are empty. Clear the table.
So it's the same task where the robot is sort of told a priori that, well, both of these cups are actually empty, so clear away the table. And from our previous model, we know that we can infer the destination of the empty cups as being the trash can. And once the robot starts interacting with for the first cup, well, it's really, it doesn't feel or filled at all. But that's not true for the second case. Now, what's happening here is that we've artificially put like a weight inside the cup. So it's actually not empty. It's actually more like full. So in that case, the robot is consuming observations from its force signatures. So the force torque sensors are giving information about the lifting force, etc. And the robot is experimenting multiple times in order to make appropriate, it's shifting its belief and trying to experiment with it enough number of times till its belief, the posterior converges to being satisfactorily, being confident that the cup is actually full, and then not throw away the cup. Right? So it actually doesn't throw away the cup and puts it appropriately, nicely on the tray, realizing that it's actually full. So the way this was sort of done is by looking at force measurements. So that's the deliberative interaction part where we can use this force signatures, and that refines our belief over the state of the symbolic constant. So remember that we put discrete variables in our world model in terms of properties. So the force signatures now, the deliberative interaction is informing our belief, and then when our belief is appropriately resolved, then our plan can continue. The capability that this gives us is robust behavior synthesis, in a sense that we can leverage this other modality of interaction to physically gather additional information to make appropriate judgments about aspects of the world model that are not available to us directly. And the model then was put also on, say, a mobile manipulation platform where it's a similar kind of an estimation happening now on briefcases to see whether the briefcase is empty or it has some contents in it. If it's empty, then it can be discarded. If it is full, then we should be careful, or we should do something else with it. And what this experiment shows is that we converge to the right belief, the right true belief after a certain number of experiments that the robot arm performs with this particular object. We converge to the exact the ground truth state. And this sort of correction can happen between what the language says. The language gives some observation of the latent variable, and then the physical interaction is refining that. Sometimes it can correct it, sometimes it can reinforce it, and that the Bayesian machinery under the hood is able to handle appropriately. So I think nearing the end of the time allocated, so very briefly, I'll just mention one other aspect, which is about all the results that I've shown so far is largely manipulation and a little bit of mobile manipulation, right? But we're extending our task or our instructions to, say, long-range traversal, say, outdoors. We are going to require models of places. So if you say, robot, take a right on the main street towards the park, we need some model of places, and being able to represent geometry, being able to represent at what distances features are in a particular place, learn that kind of prior distributions is going to be important. So this work way back actually in this ICRA 2010, but the central idea there was to learn in a sort of a self-supervised way a model of spatial distributions. So what we are learning here is distances at which certain features occur. So doors occur, or windows occur at certain kinds of distances. And that helps us to robustly recognize when certain aspects of the place have moved away and certain aspects actually remain. So this was done in the context of place recognition, but shows, again, it's a form of common sense knowledge, like a self-supervised way in which we are acquiring knowledge about what the world really looks like, and then robustly recognize places as we approach them. So there's much more work to be done in terms of more robust place models moving forward, and I think that's an interesting avenue explore for future. So we talked about language understanding, intent, inference, and then we talked a little bit about background knowledge as being central to be able to resolve certain instructions. And the work that was described essentially is adding constructs into the world model. It was adding constructs in the sense that there was a certain conceptual substrate that needed to be added, and then ways to infer the specific state of these constructs to be able to finally synthesize appropriate behavior. So all of that machinery, in some sense, has allowed us to so today we are capable with those tools to be able to perform simple forms of teaming, where we have instructions providing some sort of a background knowledge.
The rightmost barrel is full.
Or some knowledge about what of certain attributes in the world model, and then the robot can take that information.
The leftmost barrel is full.
Go and execute the plan, and then refine the plan, correct it appropriately with interaction and how the scene is evolving. So this is the integrated experiment under the RCTA program that concluded last year, where the robot is getting a high-level instruction and then some situational awareness, but that's that needs to be refined, and then the robot is able to do that. So that's the kind of capability that field robots today have. So we've reached that stage where simple forms of teaming is possible. But there are more challenges when we come to more complex forms of teaming, right? Where, let's say, in a factory kind of an environment where the human would like the robot to bring all the parts to assemble the engine, right? And then the robot might need to reason about what things are actually required, and might also notice that the person has started assembling the base of the engine, and that might start trying to help proactively in finishing that assembly. That ability to recognize plans and being able to proactively respond is still challenging. It's still beyond many of the tools that we have today. And similarly, let's take an outdoor kind of a mission where we would like the machine to be able to understand things like, okay, go to the back of the building, tell me when you see a vehicle coming. If the vehicle comes, then can you give me cover, or can you keep me observing? Be able to reason with high-level constructs of approach or being visible, and then simultaneously respond to how the environment, how the commander is responding. So those are still difficult, and those will require still further advances to be made in the kind of world model we have. So this is the last slide, and there are many challenges, and a number of researchers are on the call, and as a community, we'll see progress on some of these in the near future. We need progress on many aspects. Let me say one or two here. One is symbolic perception or complex perception, right? When are you approaching, being able to recognize when people are entering, exiting, some of that behavior and more complex interactions about what all is inside a particular object, etc. Those kinds of symbolic constructs are still difficult. And the other one where I think a lot of progress is needed is representation amenable to reasoning. So having planners which can reason both about the cognitive or the symbolic construct as well as low-level motion plans is like a big gap that still exists, and that is going to be fundamental in being able to scale up to more complex teaming missions in the future. So I would like to thank all the wonderful collaborators at MIT, and before that at Oxford, and now at IIT Delhi. And I'm grateful for the support by funding agencies. And thank you for your attention. If there are questions, I can take those questions now. Thank you.
Thank you very much. Shall we take questions? Any questions?
Rohan, I have a question. Thank you for the talk. The last slide that you had, I was looking through the list, and one of the items was causal models for physics and models of causality and physics. So this goes in the opposite direction with respect to the learning-based methods that you were mentioning. before. So why do we need models for causality in physics essentially here? How would they provide value?
Okay, so the question is about causality in physics and why causal reasoning can benefit. Well, I think it can be of use for the following two reasons. Let me talk about physics first, right? So if we have good representations of physics, we can do things which are sort of hard to do, right? So let's say we are trying to do throwing. Recent work has shown that throwing, we have now a good model of throwing. Let's take bending, right? So let's imagine where you would like to bend a piece and construct a tool to appropriately then fulfill a task. Now, presently, we won't be able to reason because we don't have a notion of bending. Similarly, sliding. Let's imagine that you have a box in which multiple objects have been kept, and the friction is so large that the only way to reduce friction is to put tires under the hood. I am able to reason because I know that once we put the tires, this friction is going to go away, right? But for a machine, until unless a robot has a model of what physically static friction is or how static friction can be eliminated, it cannot synthesize that plan. So that's the reason why physics is sort of important. Now, in terms of causality, there are various ways why this is likely to be important. One is, in a sense, when we are understanding some aspects of behavior. So let's say we have a robot trying to assist in say a medical kind of a setting, like in a hospital. And if you see the nurse is trying to bring a thermometer, then you should be able to make some sort of a causal reasoning or causal connection that, well, there might be a patient whose temperature is to be measured, and you can start sort of anticipating what are the other things that might be required, right? So there's that kind of an abstract causal thing that we don't have constructs for. Like, I've not shown any examples where we are doing that. And in some sense, causality also helps you to do the counterfactual reasoning later. So what if kind of questions. So if I know the cause-effect relationships, I can project plans forward and prune away the plans that are not going to be compatible with the goal state that I'm trying to talk about. So being able to do counterfactual reasoning is still hard in this association-based learning that I described, which is largely semantic construct, low-level constructs trying to learn association. What if kind of a reasoning, being able to see how the world will evolve and then decide, that's where we need models of causality.
Okay, just a quick follow-up on that. It seems the talk largely had, and correct me if I'm wrong, a representation from a perception perspective, because like, let's say towards the end of the talk, there were examples of spatial knowledge and representing spatial knowledge for human-robot teaming. But it also depends on action. The robot can modify the environment with its action. So we should be reasoning about both action and perception with it when we are modeling the environment.
Absolutely. I think that's extremely well said. And there's two things there. One, the work in the tool prediction is actually goal condition policies. So they are in some sense conditioned on the task. So that's one area where the representations are tied to the task at hand, right? So representations in isolation is, I don't know if this jury is still out there, but task dependence, what you're trying to accomplish, being able to do representations for that is likely to be very useful. I think the other part, what you're hinting at, is leverage interaction much more, and I think that's very crucial. So what we're saying here in terms of lifelong model building, let me highlight this here, right? So this part about lifelong model building, this is about the fact that, well, you have a situated agent, right? So at night, it should be fiddling with objects and trying to learn richer models of that. It has all this time. It should be introspecting. So the work on introspection from Oxford, it talks about being able to refine pieces of the world model where the robot does not really have a good predictive model, going back and refining, as well as the recent work in curiosity, right? Where use this time to learn, say, improve the world model, assuming a certain distribution of the task, a set of goals later on. I think that's going to be crucial. So, ideally, I would like the robot at night to be able to experiment with certain things, say how things can be used, how things cannot be used, learn an appropriate dynamics model, etc. And in the morning, explain to me what it has done, and hopefully it will become better over time. So I think much more interesting work lies ahead. Some of this we have seen in pure RL setting, but translating that to these scales, I think there's a very interesting work to be done there.
Yeah, I agree. Thank you for the talk. I enjoyed it.
Cheers.
Other questions? There's a question in the chat if you want to take a look at that.
Yeah, so I think the question is from Alex. Let's say if the system has a representation of the way a particular tool is used, a cup for drinking or a tray for carrying, and then you introduce a new object, a mug or a cup carrier, and it observes a human use it, can your system infer that the new object is a cup or a tray, or that the use of the new cup object maps onto the same structure that cup tray does? I would like to be just to hear your thoughts about whether the architecture you described could be extended to some ethical constructs. Okay, so I think there are many things that might not show that I understand all of it, but I think in the work that I talked about in terms of generalization, the generalization was being able to predict the utility of a tool for synthesizing a particular plan. So if you see a cup, we assume that the type cup has been identified, even if it's not been seen in training, but the purpose of the tool of the cup as being able to carry a certain contents and being able to transfer those contents, that is being inferred by this, because what the concept net or dense embeddings do is to relate what task, what actions can be performed by a particular object. So I think that sort of partly answers that question. The other thing you're saying about ethical concepts, and I think that there's a deeper thing there. I think again, that's sort of there in the last slide. So learning very abstract constructs, right? So for example, learning abstract constraints that you don't enter people's bedroom, right? I think that's one kind of an example that can you infer that kind of constraints. I think the learning is generally if you have the data for it. I think there's interesting work from Devi Parikh at Georgia Tech where she learns very abstract constructs or how people's mental states change when you become fearful or angry, etc. So she's shown being able to learn that through abstract stories. So cartoon stories, etc. She's able to infer relationships from that. I think Eugene Choi at University of Washington also has a similar work around that. I think if you have the data for it, then we can do it. And I think unfortunately robotics is, in our land, is deficient of the kind of data which is like more easily available in NP and other communities. So if you have the data for it, I think some of those techniques could be applicable there.
I guess my concern is that you've convinced me that this domain is AI complete. I have to solve everything in order to make progress.
Is it?
Especially that list of technical challenges. I mean, that's basically solve AI.
Yeah, I think maybe I should tone it down. That's not a good way to approach a tenure track. So we're saying, well, I think no. I think what you're saying is, I think there's a deeper, underpinning to what you're saying. You're saying that I need everything in order to make progress. Now, I think it's dependent on the capabilities of the robot, right? We have our robot capabilities are fairly constrained. We can largely go from point A to point B. We can do grasping. We can look at things, right? So the kind of task that we can do is sort of constrained with that. So I think whatever task that we would like the robot to do, we should back out what are the concepts that are needed. Obviously, if you had all the constructs in the world, maybe we had all of psych in the robot set, we should be able to do everything, but that's a little challenging. So I think, building off what the comment was earlier, we are dependent on the kind of tasks that we are doing, the action space of the robot. Condition on that, we should extract constructs and have some mechanism of acquiring those constructs. I would sort of say that like a goal conditioned or robot constrained AI complete, maybe something of that kind.
I'd want to think about briefly an alternate approach that tries to avoid this AI completeness. And it's basically based on the idea that there's nothing new under the sun, and that everything humans want to do, it happens so often and it's so stereotyped that if we could just collect up, all the likely scenarios and recognize which scenario we're in, we don't have to be very smart. And this is basically a restatement of the script hypothesis. I think Roger Schenck was an early proponent. You go into a restaurant and you ask for a menu and you order stuff. And I'm actually able to function in Japan without speaking a word of Japanese because of those scripts. I can walk into, basically their equivalent of 7-Eleven, the Circle K stores, and I can get lunch. And I even can understand when the guy says, in Japanese, do you want this microwaved or heated up? I know that's when he's going to ask me that question. And I know to say yes, even though I don't understand the question. And this works really well. And it's not AI complete.
Yeah. So I think maybe inductive generalization, right? So we to have the ability to generalize somehow, I think needs more thought. Like, do we keep all the data around? Do we extract or distill knowledge? How much do we distill knowledge? It's a challenging thing. Not sure if I have more meaningful things to say there.
So we had a recent job talk by someone who had applied nearest neighbor approaches on the scale of billion, a library of 1 billion kind of things. And that helped the translation. And maybe nearest neighbor approaches could help deal with these problems.
Probably it is. So I think in navigation, if you look at navigation, I think the navigation tasks, large-scale localization mapping have taken a lot of very data-centric approach, right? Thousands of kilometers of driving data, and where you don't have data, you collect data and then appropriately, do with that. Maybe that's the way forward. Maybe every data point is its own variable. We don't need to consolidate abstractions. But I think there is certain appeal to abstractions. There's at least weak evidence that the brain is doing some sort of hierarchical, at least there's some abstractions there. So there might be some things there. So in the limit, yes, nearest neighbor is, if you can retain all the experience and maybe retrieve that, is probably useful. But there's something to be still said about abstractions that allows to generalize. So I think the jury is still out.
So maybe there's a happy medium of limited abstraction or local abstraction.
Possibly.
Well, thank you. Any other questions? Well, thank you very much.
Thank you.
And the recording's going to end up on the web, so lots of people are going to be able to see the talk. And I thank you for contributing.
Thank you.
To the sort of material that's out there for everyone to look at.
Thank you very much. Really appreciate it.
All right.
Bye-bye. Thank you.
Bye-bye.